Problem 1 from 2002 is kind of interesting in that I think it starts off more difficult and then as it goes it actually gets easier. We have a linear charge distribution centered around an origin 60 degrees above, 60 degrees below. They give us the linear charge density 1.5 times 10 to the minus 5th coulombs per meter, and they give us the radius. First thing is determine the total charge on the rod. If we multiply the linear charge density by the length of the rod, then we should be able to figure it out. Since we have 120 degrees, we know that that's a third of a circle. So we need to multiply by a third of the circumference. The length is 1/3 that of the circumference, so 0.21 meters. Here I'm multiplying the linear charge density by that length to get the total charge. I get a total charge of 3.1 times 10 to the minus 6 coulombs. Now the hard part is actually determining the magnitude and direction of the electric field at the center O of the arc, okay? Should be easy to figure out the direction of the electric field because it's positive, so all of the Y contributions are going to cancel each other out. We're only going to have an X contribution, so that should be an electric field that's pointing in the east direction. I have a ton of dog hair all over me right now. In the east direction, so make sure to get a point there. We need to set up our integral k dq over r squared. Remember that we always replace dq with dl times lambda, small length contribution, small charge element, times the linear charge density. In this case, the length is going to be the arc length, r times the cosine of theta. That's how we're going to get k lambda cosine theta r over r squared d theta. This allows for an integral over d theta from negative 60 to 60. Go back and check over your notes. We did this before for an electric field. We maybe just didn't use this exact angle measurement. We should get an electric field along the x direction of 2.3 times 10 to the 6th newtons per coulomb. Now I know I did that really fast, but remember, you got to do the substitution. Small amount of charge, small amount of length times the linear charge density. We need to transform that into an arc length based off the cosine of theta. We need the cosine of theta to get all of those x contributions. Hopefully this is straightforward. Dramatic pause on this one. Okay, the rest of the problem is actually very straightforward. Next part, they're asking us for the electric potential at O. Remember that electric potential is a scalar quantity, so we don't have to split it up into any vector analysis. It's just kq over r. Every charge is the same distance away, so it's just k multiplied by the q that we found before divided by r, 2.8 times 10 to the 5th, volts. Again, that is a very straightforward problem. Don't get tripped up on that. Finally, we have to determine the magnitude and direction of the force that must be applied in order to keep a proton at the origin at rest. The proton is going to want to be pushed away by this positive charge, so the force that we have to apply to keep it at rest has to be west, okay? So make sure that you don't read that too fast as the force being applied to the proton. It's the force necessary to keep the proton from moving. That's going to be the charge of the proton, 1.6 times 10 to the minus 19, multiplied by the electric field that we found before, and that's going to be in a west direction. Finally, the proton is now released. Describe in words its motion for a long time after its release. Now be careful on this. It's going to have the maximum amount of force at this position. As it gets further away, that force is going to decrease. But what that means is that this proton is always accelerating. It's always feeling a force in the same direction. And even though that force is reducing, that means that this thing is still gaining speed. So what you can say is that it's moving east and it's getting faster and faster, but the acceleration is tapering off. So it's getting faster and faster at a slower and slower rate. So accelerate east, continues to gain speed, acceleration will decrease to 0 eventually. But it is speeding up the entire time that it's moving east. Really think about that concept. Just because the force is decreasing, you still have an acceleration, so it is still gaining speed as it moves east.